everyone. Welcome to the course Digital Control in Switch Mode Power Converters and FPGA-based Prototyping. We are in the week 2 problem solving session. So the week 2 is about fixed and variable frequency digital control architectures. Okay, let me share my screen. Let me know when you can see my screen. Hello. Hello. Yes. Okay. So we are in the week 2 problem solving session of this course, which is fixed and variable frequency digital control architectures. So I am Teja Golle, third year research scholar working under Dr. Santanu Kapat at Embedded Power Management Lab, Department of Electrical Engineering, Indian Institute of Technology, Kharagpur. So just to summarize what we have discussed in the last week, which is about introduction to digital control in switch mode power converters. In the last week, I have given a brief description about introduction to digital control, why we are going to digital control, what are the advantages, what are the challenges that we'll be facing in digital control. And then I have discussed about commercial digital control IC. And I have discussed what control architecture they are using. It is basically about multi-phase buck converter. So this was basically regarding multi-phase buck converter. So this IC I have discussed few aspects of this IC. And then I have shown the hardware prototype that SAR has used in this course. Again, I will be discussing about this hardware prototype briefly in the upcoming weeks when hardware will be shown. So I have discussed what are the major components of the hardware in the power stage as well as signal conditioning stage. I have shown where ADC and DAC are there and how the converter is communicating with FPGA. All those things we have shown in this hardware prototype. Then I have discussed some aspects about FPGA, what architecture FPGA will contain, and what are the major building blocks of FPGA, how is it different from ASIC, what are the advantages of FPGA versus ASIC, and what are the disadvantages, the trade-off between these two. I have discussed in the last week. And then I have discussed about control techniques, and majority of the students are still facing issues. So again, I'll be discussing in this week, I'll be discussing about these control techniques as well as the sampling methods that are going to be used in this throughout this course. So I'll be discussing about sampling techniques of a different digital control architecture. So when you have doubts, you can ask when that particular control architecture has come. So at that point, you can stop me and you can ask any question. And then last week I had discussed about the digitization of control loops, how we are digitizing single loop control, how we are digitizing two loop control, what are the ways of digitizing two loop control, whether we are going for mixed signal or whether we are going for fully digital, what are the challenges. All these aspects I have discussed. And then I have shown a power stage design of buck and boost converter, how we'll design in the current capacitor of buck and boost based on the report. So coming to week 2, which is about fixed and variable frequency digital control architecture. So first I'll be discussing about some sampling, basics of sampling. So I'll be discussing about what sampling techniques that we are using and where exactly we are sampling and what we are sampling. We usually sample output voltage. So all these aspects we'll be discussing. And then I'll show about voltage mode control digital pulse width modulator. These architectures, how that closed loop is working, and what are the different architectures that we are going to use, and what type of sampling we'll be using in this voltage mode control. And in DPWM architecture, so there are 3 architectures that I will be discussing. I'll be discussing about the hardware, how to implement DPWM architecture, and in this course throughout we are using counter-based DPWM. So I will explain how counter-based DPWM will work and what are the bottlenecks of counter-based DPWM in that. And in fixed frequency current mode control, I will discuss different architectures, mainly peak as well as valley, and what are the sampling methods that we are following in peak current mode control as well as valley current mode control. And in variable frequency, we have different architectures like constant-on or constant-off. So we'll be discussing about this, and then hysteresis control also I will be telling, and what sampling methods, what is the architecture of the closed loop of this digital control architectures we'll be discussing. And then let's solve few problems. I have made few problems, so we can solve few problems together. So coming to the basics of sampling, we'll discuss about fixed and variable frequency modulation. So let us consider trailing edge modulation voltage mode control. I have discussed this in the last week as well. So here what we are comparing is this VCon is coming from this output feedback. So if you consider V reference, we are getting this V feedback from V0. So here there is a resistor divider. In the actual implementation of the hardware that SAR has used also, we are using a resistor divider so that the voltage will be R2 by R1 plus R2 into V0. So we are stepping down the voltage so that it falls in the range of the ADC input. And we are subtracting it from V reference. And then we are using a PID controller, GC objects. Now I am writing in analog domain, but digital domain, it will be GC object. This will be giving VCon. So that VCon is being compared with VRAM, and that QC acts as a reset signal, and the set is coming from the switching frequency because this is fixed frequency, and that will give us Q. So this is the switching frequency, and this is the inductor current. So we are comparing the ramp. So the ramp will be something like this. So we are comparing this ramp with the control voltage. The control voltage is something like this, and it is generating the closed loop gate pulse for this buck converter. So one question is what exactly we are sampling and why we are sampling. So let me change the color of the band. So this V feedback is going to digital. So this V feedback, so let me draw it here, that V feedback is going to ADC. V feedback. Now this digital pulse is going to FPGA, where we have a summer block. So this is minus and this is plus V reference. And after that, this GCZ will come. So here we will have another block, which is a PID controller digital. So we are mentioning in GCZ. So now we are talking about this ADC. So this V feedback ADC will have some clock frequency, say F ADC. So how fast are we sampling V feedback, and where exactly are we sampling V feedback, and why we are doing so? That we'll be discussing in the upcoming slides. So I'll be discussing about 4 different cases. In the first case, we are sampling the output 1 sample per cycle. So here is 1 sample, and here is 1 sample, and here is another sample. So this is the switching frequency, fixed frequency. We are considering trailing edge voltage mode control, and we are considering.
Hello, sir.
Hello.
Hello, sir. Sir, what is the clock frequency here?
So here I am not mentioning, but in the hardware that we have used, the clock frequency is 100 megahertz.
100 mega.
100 megahertz. So we have used Spartan 6 FPGA, which has 100 megahertz clock. So using this 100 megahertz clock, we are generating the other FADC and FDAC if we are using DAC in the case of current mode control, but in voltage mode control, we don't need DAC, and switching frequency in fixed frequency. So from this, we get these clocks, other clocks, and how we implement that we'll discuss in the 7th week, 6th week, and 7th week of this course. So for fixed frequency, this is the pulse, and we are sampling, as I told, one sample per cycle. And by we are taking 1 sample per cycle, we are updating the VCon, so V0, and then V reference, and then GC object, and then VCon. So this is V reference plus minus V0. So we are taking V0 once in a cycle, and it is being updated in once in a cycle. So say the voltage is something like this. We are taking at one switching frequency clock, and then it remains constant for the next cycle, and then again at the next switching pulse, we are taking the sample, and it remains constant. And using this V0 of n. So
Hello, sir.
yes.
Can you tell me about the V reference?
So V
How you
reference is
define
the
V reference?
reference voltage. So we are operating this in a closed loop. So the voltage at which you want the buck converter to operate at the output side. So if I want the yes,
suppose I have buck converter,
yes,
the output voltage of buck converter is 5 volt. Then what is the value of V reference?
V reference. Okay. So
Yeah.
say this V reference, you want how much voltage? 5 volt, right? But I am giving V feedback to the ADC, not the V naught. So V feedback will be R2 by R1 plus R2 into V naught, right? So my V reference dash that I should be giving should also be scaled down. R2 by R1 plus R2 into V reference. The V reference that you want is 5 volts. So now what we are doing is, so this V feedback, we are regulating it V reference dash. By doing so, V naught that we have here, it will be regulated at 5 volts.
Okay.
Understood. So what R1 and what R2 SAR has used and what is the ratio that SAR will be discussing when he'll implement in the hardware.
Okay. Okay, sir.
So in this case, we are only updating once in a cycle, but now you may ask, like, we are taking one sample and it is constant for the entire cycle, and then we are updating. Can we increase? Yes. Now here we are considering 4 samples per cycle. So this is FSW. Now the FADC is 4 times of FSW. So V naught is being updated for 4 times in a cycle. So if you consider one switching cycle from here to here, we are updating 1, 2, 3, 4 times. So it is being updated 4 times in a cycle. So now here, what is the ADC requirement? FADC is FSW. And here we need FADC 4 times FSW. So we are increasing the ADC computation. We are sampling the output voltage 4 times in a single switching cycle. So the ADC will convert V naught to V naught of N. Sorry. So the ADC will, sorry, let me move the pen. So V naught is converted to V naught of say K 4 times in a switching cycle. So here we are using ADC 4 times in a cycle. We are using ADC 4 times in a cycle. So it will increase the power consumption of ADC, and we need more power. So there is nothing wrong by updating V naught 4 times in a switching cycle. Say if we are updating 100 times in a switching cycle, then V naught of the N digital will be almost close to the analog. So it is like in the digital also, we can almost get it in the analog. So it will be very small steps. So we can almost track the analog input voltage. But whereas in the case of once sampling per cycle, we'll get something like this. So here we are taking sample. So we are taking the sample and we are holding the value for the entire cycle, and then we are taking another sample. We are again holding it. But if we increase the number of samples per cycle, it will the ADC will draw huge power and it will increase the power consumption. So for that only reason, we do not do many samples per cycle. Also in the commercial products, they will sample only one sample per cycle. So now we are considering here, we are taking the sample at this point, and we are assuming that V naught of N is available at that point. But ADC needs some conversion time, as well as this GC of Z. It also needs some computation time. So the moment you are sampling V naught and the moment you are getting VCon, it actually needs some time. Say we are naming it TS. So if I want the VCon to be available here, I have to sample it TS time before. So that's what we are considering here. So we are sampling it TS time before this point. So this TS, we are considering 2 components here. One is conversion delay or conversion time plus computation time. So this conversion time is for the ADC to convert analog voltage into digital, and this computation time is for the FPGA to generate the VCon signal. So it needs some time. So we are assuming TS delay. So we are taking the sample TS time before. If you see FSW as well as FSAP, they are both are fixed frequency, and we are taking sample once in a cycle, and they are time shifted by time TS. So we are using interval 2 sampling. Why interval 2? So we are sampling in the falling edge of inductor current. So during this time we are sampling the V0 in every cycle, once in a cycle. And so here we are taking the sample. Now after the sample is taken, the ADC will convert analog signal to digital, as well as that error V reference minus V0 will be carried out, and then it will be passed to digital PID controller, and then we'll get VCon by the end of this cycle. So at this point, we have this VCon. Now again, the TS time delay depends upon the conversion time of ADC as well as the computation time. So different ADCs will have different computation time, and if you go for flash ADC, it will take very less time. But if you consider some serial ADC, then the time increases. So the conversion time depends upon the what ADC you are using. Say sometimes we use serial ADC, sometimes we use parallel ADC. So it takes some time, and depending upon the time it takes, say if the time is very less, then the cost of the ADC will be more, and if the time is say serial, then comparatively the cost of ADC will be less. So again, we have to decide whether this TS is available or sufficient or not. Again, it depends upon how much time it takes for it to convert the analog to digital signal, as well as the computation time. Computation time, FPGA, we are using F clock of 100 megahertz, which is 10 nanoseconds each switching cycle. So the conversion of V error to VCon take few cycles. So I say it will be taking few tens of nanoseconds, which is very less. The main conversion time actually dominates the TS delay. So it depends upon two things. One is the what kind of ADC, the architecture of the ADC that decides the conversion time, and the clock ADC, FADC. So it is dependent on both. If we increase FADC, then the switching frequency will increase, the power consumption will increase, and depending upon the architecture, the TS will depend how much TS. So usually in commercial products, they take 1 cycle delay. So they sample V0 here. So they sample V0 here, and they use it for the next cycle. So they're taking sample, say at NT, they're sampling, they're taking the sample of V0, but they're using this entire 1 cycle duration for computation as well as conversion. So this entire duration, so this entire duration they are using for computation as well as conversion. Computation. Now you may ask me, as it is getting delayed, will it have any effect? Yes, it will have effect on the stability. How TS is going to affect the stability, that SAR will be discussing when he'll be showing the MATLAB results. So it will be in the next week. So many commercial products use.
Sir.
Yes.
Sir, one doubt, sir.
Yes.
So for the interval 2 sampling, the sampling should be in the falling edge of the inductor current, no?
Yes, yes.
But here, the second figure, it's not showing that the sampling is happening in the
Yes,
rising
yes.
edge only.
I'm coming to that point. Yeah, good question. So we usually do not take sample at switching frequency because it will have some noise here. So here there will be noise. Sorry, here there will be noise. So at switching there will be noise. So usually it is not recommended to take sample at the V0. So because if we take the sample, it will have noise. So if you want a very clean sample, we take just some time before it. So we take the sample here. Also, we take the sample here, just somewhat before. So even though we are showing it here, we in the actual practical situation, we will not take the sample here. We will take just before this. So there will not be any switching noise, and the sample will be clear. So in that case, we are taking the sample in the interval 2. I mean the following. So that's why interval 2. So again, like the ADC decides how much cycle delay has to be considered. So one of my friend is working with ST, where he is considering 2 cycle delay. Sorry. So they are having 2 cycle delay. So the V0 that they are taking sample here will be used to will be used as weak point 2 cycles later. Again, why they are taking 2 cycles? The ADC that they are using, they want it to be very less power consuming, and the based on the architecture and the switching frequency they are considering, the ADC needs 2 cycles amount of time. So the ADC need 2 SW to convert V naught from V one. So they are using that. Again, when we are going for low power application, the ADC the amount of power that ADC is consuming actually matters, and depending upon that, they'll consider. And usually 1 cycle delay is followed widely in the many commercial products. So whatever SAR will be discussing, it is based on 1 cycle delay. So this is about the trailing edge voltage board and fixed frequency. So I have given one example of fixed frequency. Now coming to variable frequency. So in this case, if you see, there is something called uniform sampling. So uniform sampling is like a fixed frequency. So f-samp is fixed. We are taking it uniformly after fixed amount of time interval. Event-based sampling is, it is triggered by an event. So this is triggered by an event. So some trigger, an event will be triggered, and that will give us the f-samp. So why we are going for event-based and why not uniform-based? Say we are operating in constant off, so this off time is fixed. On time is variable. If we take the value point, so this is the value point, this is the value point, and this is the value point. So the time difference between these two value points, T1 and T2, it is not fixed. It is varying, right? Because it is variable frequency. Only off time is fixed. But if you are considering a constant frequency with which you are sampling the output voltage, the difference between this point and this point in this cycle, and the difference between this point and this point in this cycle, say this is TS dash and this is TS, and the difference between these cycles, TS double dash, it is not same. So TS is not equal to TS dash and TS dash, and it is sorry, this is not equal to TS double dash. So I'm trying to say this is not having a constant delay with respect to this. So sometimes it might be far away, sometimes it might be closer. So we are not actually not synchronized with the main clock. So this will lead to limit cycle oscillations. And also there is another issue. Say I'm drawing this value points at which the value point is occurring. It is a variable frequency, right? So sometimes it may be closer, but sometimes it may be very far. And sometimes it may be very closer. And sometimes it may be very. Now let me change the color. So this is this FSW here. Now if I'm drawing this F sampling, if you are using fixed frequency, say I'm using fixed frequency. If you consider from this cycle to this cycle, I am taking a sample here, I'm taking a sample here, I'm taking a sample here. And in between, I'm taking only once from, as the time period is more, I'm taking more samples. And when the switching happens frequently, then we are not taking any sample in this cycle. So this is not uniform, and this is not recommended. So in fixed frequency control, the frequency is same. So we go for uniform sampling, which is also fixed frequency. And in the case of variable frequency, we go for event-based sampling, because uniform sampling is not happening in every switching cycle. It may or it may not happen. That's why we are not going for uniform. It might lead to limit cycle oscillations that Sar will be showing when he simulates in MATLAB. And why we are going for event-based? Because it is triggered by event. Say in constant off time, it is peak, right? So whenever it is hitting peak, then we are triggering the constant off time. And whenever it is hitting the other peak in the next switching cycle, again, we are triggering the constant off time. So this hitting the peak is the event. And this event happens once in a switching cycle, right? So we are taking the sample. So again, we are taking the sample once in a switching cycle. Whenever this it is hitting at this event. We are taking the sample. So now it is guaranteed that we are taking only once in a switching cycle. So we'll update V naught once in a switching cycle. So that's why in variable frequency we used
Sir?
event-based. Yes.
Sir, how we will come to know that the inductor current has reached the peak value?
So that is the architecture of constant off, right? In constant off is analogous to peak current mode control. So say this is off time, T off, it is constant. So after the off time is ended, we turn on the inductor. And until what point we turn on the inductor? Until it hits the reference. So we are talking about constant off time current mode control, not voltage based. So current based control we are discussing about. So whenever this inductor hits this reference, that will reset. So this is the reset pulse. So that will reset, and again constant off time it will be off, and again after at the end of constant off it will be turned on. And what time it will be turned on? Until it hits the peak. So this is the event, and it has to hit. Until it hits, we'll keep the inductor inductor current on. So it will increase until it hits, and when it hits, it will be for constant off. So this event will be happening in every cycle, and that is what we are considering as reference to sample the output voltage. Is that clear?
Yes.
So that is just a basic introduction about uniform sampling as well as event-based sampling, where we are using uniform sampling, where we are using event-based sampling. Coming to voltage mode control. So first we'll discuss about voltage mode control, DPWM architecture and its sampling techniques. Then I will go to the DPWM architectures. So first coming to voltage mode. There are two, okay, is my entire screen visible for you? Okay. So this is trailing edge voltage mode control, and this is leading edge voltage mode control. For your reference, I'm showing leading edge. Sir has also discussed this in his lectures, but usually in practical application, like leading edge is not used. We will go for trailing edge. So in trailing edge voltage mode control, so we have this RAM. So in analog, it is a smooth RAM, but in digital, it is a counter. So we have these steps. So this is counter based RAM. So this is the RAM, which is counter based RAM. Counter based RAM here. And this VC of n-1 and VC of n and VC of n+1. How these are coming? These are coming from the output voltage. So there are three terminologies that you have to consider. One is trailing edge. So what is trailing edge? So when the switching frequency sets, whenever it is setting, so it acts as a set pulse, right? And this event acts as a reset pulse. So switching frequency is acting as a set here. So it means trailing edge. Also in current mode control, if you see peak current mode control, the inductor current is trailing the reference, right? So inductor current is trailing reference. So it is also trailing edge. If you consider valley current, the inductor current is leading reference. So inductor current is above. So this is called leading edge. So that's how we define trailing edge, leading edge. See here, if you consider leading edge, the switching frequency, it is resetting. The switching frequency is acting like a reset. And whatever that is coming from the loop, that is acting like a set. So it is, since it is resetting, we call it leading edge. So this is a trailing edge, and this is leading edge. Just an announcement. So I am using a normal Zoom version meeting. So the meeting time is limited to 40 minutes. So after every 40 minutes, the meeting will be ended. I'll again join. You also please join in the same link. So now there is a less than a minute. So within less than a minute, this meeting will be ended, but join in the same link where we'll continue. When I upload the YouTube video, I'll merge all the videos, and it will be a single video. So within a minute, this meeting will be ended suddenly. You try to join in the same meeting, and I'll continue from this slide. And so we have understood about trailing edge as well as leading edge. So what is trailing edge? What is leading edge? Now we have to come to interval 2 sampling as well as interval 1 sampling. What is interval 2 sampling? What is interval sampling? Interval 2 sampling, it happens when it is off. Okay, so whenever we are taking the sample when hello.
Yes, sir.
Yes.
Okay. I'm sharing my screen. Let me know when you can see my screen. Is my screen visible?
Yes.
So we are discussing
Yes.
about trailing edge as well as leading edge. So I have discussed about trailing edge, what is trailing edge, what is leading edge. So interval 2 sampling is we are taking sampling during off time. So when inductor is falling, at that time we are taking the sample. And interval 1 sampling means whenever the inductor is rising, during that time we are taking sample. And you have understood 1 cycle delay. 1 cycle delay means the V naught that we have used in this cycle will be used to generate V count of n in the next cycle. So the V naught that sample has been taken in this present cycle will be used in the next cycle. So that conversion plus computation time, you can say, is delayed by 1 cycle. So if you see here, the V naught of n is happening here, right? If you can see, they are naming it is V naught of n, and VCN of n is here. So these two are related. So n, right? So V naught of n that is happening at nt is used in the next cycle, in the n+1 t cycle, and it is a VC of n. So there is 1 cycle delay. If you see, there is this 1 cycle delay, isn't it? Have you understood how 1 cycle delay is coming? Hello.
Yes.
Yes, and you may ask, sir, why we are taking sample here? How can it be interval 2? As I have discussed, there will be switching noise. So usually we do not take the sample here. We take just before that. So we take sample here, which is the interval 2 sample. And this is just like a mirror image. So trailing edge we are considering. So here it will be leading edge, and this is interval 2 sampling. So this is interval 1 sampling. How it is interval 1 sampling? So V naught of n. So V naught of n that is happening here again is used to generate VC of n in the next cycle. So if you see this delay, it is again 1 cycle delay. And we will not take the sample here because at every moment when the switching happens, it will inject some noise, and there will be some noise coming at V naught also. So usually we do not take at this point. We'll take some just some time before. And this is very less negligible. So again, we are taking in interval 1. So whenever inductor current is rising, we are taking. So this is interval 1 sample. So this is someone has asked. So what is the minimum sampling frequency? Okay, and can others see what he has asked? Actually, last week when I was taking the session, people were only sending messages to me, so others were not able to see. So if you ask any question, make it visible to others so they'll know. So one student is asking, what is the minimum sampling frequency? So minimum sampling frequency is the switching frequency. So F sampling minimum is F switching frequency. Why? Because we have to take the V naught sample at least once in a cycle. If we take sample, say once in 2 cycles, say we are taking once in 2 cycles, then it will lead to subharmonic oscillations, which is also kind of instability. So at least once in a cycle is mandatory to make the system stable. And because if you are taking 2 times in a cycle, like once in 2 cycle, you are not taking sample in the middle cycle. Like 1 cycle you are skipping, and the next cycle you are taking. 1 cycle you are skipping, and in the next cycle you are taking. So what this happens whenever you are not taking the sample, you are not regulating the V naught in that cycle. So V naught will become somewhat unregulated in that cycle, and it will lead to subharmonic oscillation. So at least we'll take once in 2 cycle. And if you want to go take 2 times or 3 times, it's up to you. It will increase the power consumption of the ADC. And if you are fine with that, then you can go for higher sampling. Again, the architecture of ADC, it depends upon the cost. So this always cost versus speed trade-off will be there. If you want high speed, the cost will increase. If you want low cost, speed will be reduced. And once in a cycle is good enough, so we'll get time of TSW time. So in any ADC that can convert within TSW time should be fine enough for implementation of closed loop buck converter. So this is about the voltage mode control. So we have considered 2 case studies. One is the trailing edge modulation, another one is the leading edge modulation. Here we are using interval 2 sampling with 1 second delay. Here we are using interval 1 sampling with 1 second delay. So now coming to the DPWM architectures. So we have seen, right? So this is the DPWM. So how are we generating this DPWM? How this DPWM conversion is getting converted into deuteration. Hello, yes.
So
Hello.
basically in this trailing edge modulation,
Yes.
can you hear me?
Yes, yes.
Sir, in this trailing edge modulation, if the actual inductor current is less than the reference, we say it is trailing edge.
Yes, actually, there are two things. One is voltage mode control, and one is current mode control. So in voltage mode control, we are comparing VR and VCon, and in current mode control, we are comparing IL and I reference. So in the case of current mode control, if IL is less than, say in this case, say IL is less than I reference, peak current mode control basically, inductor current is trailing reference. So we call it trailing edge modulation. Whereas in the case of valley, whenever it hits the valley, whenever it hits the valley, then we are turning it on. So here inductor current is leading, I reference is trailing. So with respect to anywhere we will say with respect to IL, here IL is trailing, so trailing edge. Here IL is leading, so leading edge.
You mean leading it is at an instant of time that IL is greater than a reference.
Yes.
That's why
That's why we are saying
leading.
because it is leading. That is just a terminology, and you have to be clear with this terminology because this is universally followed, and in the exam also sometimes we may not say valley current mode control. We'll say leading edge current mode control. We have to understand that okay, leading edge is valley because IL will be always. So we have to be thorough with this terminology. That's why I'm spending some time on explaining this terminology. And you might be also asked like
PSW.
Yes, TSW is
Okay.
time period. So FSW is the switching
No,
frequency.
that
TSW.
we need to have a ADC which has the conversion frequency at least of TSW.
Yes, or like say you are using a one ADC. So like ADC conversion depends upon FADC, right? Hello, the frequency at which you are
Right,
taking
yes,
sample.
sir.
Yes. Say if the time is more, then you have to increase FADC. Then as FADC is increasing, so it is taking sample at a faster rate, so that will give you the V naught of n at a faster rate. But this again, this will increase power consumption as we are using ADC multiple times in a single switching cycle. The trade-off is always there. So this switching frequency versus this architecture versus the cost as well as speed. So if you want high speed, you have to increase the frequency, which will increase power. Also, if you want high speed, you can go for a better architecture / ADC where the cost will be
Hello.
increased. Yes, hello.
If you're saying time increases, FADC increases.
No. Actually, the conversion time. Okay, so let me write here. So the conversion time, it depends upon FADC. So if you want less conversion time, you have to increase the ADC frequency. So then as it is sampling at a higher rate, it will take comparatively lesser time. So if you want lesser conversion time, you have to increase FADC. That's what I'm saying.
So like trailing edge means whenever IL it's the reference, switch will be off, right?
Yes,
That
yes.
is
Trailing
so
edge.
inductor is trailing
Yes.
so that only inductor is positive in the control structure,
Yes.
while in leading edge inductor whenever it is goes beyond the like it has the lowest point of the reference, like it goes beyond, switch will be on, right?
Yes.
Yeah. Okay. Fine. Okay. Fine. So, what you written F sample minimum is equal to FS.
FSW. So one student has asked what should be the minimum sample, like how many samples is the minimum
Okay.
that I have to take. I told him one sample per cycle is enough, because if you are taking once in a 2 cycles, it will lead to something called subharmonics, because you are skipping one cycle, right? You are not controlling voltage in that cycle. So it will lead to something called subharmonics that Sir will be discussing in the next week when he
Yeah. Okay.
shows the magnet simulation. And that's a once in a switching cycle is mandatory. You can take 2 times, 3 times, that will increase the power consumption. But once in a switching
One more
cycle.
question. One more question.
Yes.
This course is full of digital.
Yes.
So we have to see the pre-quiz course in that NPTEL.
Yes,
That
actually,
model should
every
be.
time Sir is discussing something, it is somewhat related to the previous course. And whenever sir
Yeah,
wants you
okay.
to go through, he will mention the link in the bottom slide. So at that time, you can
Bottom
go
side,
through
sir.
that particular lecture. And I'm telling not to him, to everyone, it is not mandatory to do that course before this course, but it is linked.
Oh.
So some of the concepts are discussed there. You don't have to go through all the videos. You just have to go through the videos that sir mentions in that particular PPT.
Yeah, when with the MATLAB model they discuss, we should be ready with that. Like whenever sir is trying with digital implementation,
Yes.
that previous course MATLAB like files you will be giving, or like we have to do that and then see this digital third week
I'm
and all
not
fully
sure. I
MATLAB
think
model.
you should talk to NPTEL whether you will get the files from
Yeah,
the
okay,
professor.
fine,
I
fine, thank
cannot
you.
give you.
Yeah,
I don't have that authority. Just
yeah,
contact
fine, fine.
NPTEL team regarding the files.
Yeah, fine, okay, thank
Okay.
you.
So this is about the voltage mode control. Coming to the modulator architecture. So I'll be considering three. One is counter based, another one is delay based, the other one is hybrid. But in the hardware implementation, we have used counter based because these are somewhat complex in the architecture, and also cost will be more, and this is widely used. So we are using counter based DPWM throughout, but for some introduction and some knowledge, we are also discussing about delay and hybrid. So coming to counter based DPWM. So as I told, in the case of analog, we'll have smooth ramp, but in the case of digital, we don't have ramp. So we'll be counting it. So in the form of steps, we'll be counting. So it is counting from 0 to NR minus 1. So we call this modulo NR counter. I'm sorry. So modulo NR counter, it counts from 0 to NR minus 1. So how we are counting, there is a main clock, and in our case, it is 100 megahertz clock. And using this, we write a Verilog code, which will be discussed in week 6, how to write the Verilog code, how to write a counter. And there we use a counter which will count for every switching clock, it will count, and the maximum is NR minus 1. Say I am using n bit counter. N bit counter. So it can count up to 2 to the power n, right? So in that case, and 2 to the power n means NR. So it is counting from 0 to 2 to the power n. So say there is 2-bit counter. So there are 2 bits, 0, 0, 0, 1, 1, 0, 1, 1. So this is 0, this is 1, this is 2, this is 3. So it is counting from 0 to 3, which is how many? 4, which is equals to 2 square. So for 2-bit, we are getting 2 square. Similarly, for n-bit, we'll get 2 to the power n. And it will count from 0 to 2 to the power n. Say if 2 to the power n is NR, we call it modulo NR counter. And this terminology is important. So when we say modulo NR counter, it is counting from 0 to NR, not 2 to the power NR. But when we say n-bit counter, so here I'm specifying n-bit, it counts from 0 to 2 to the power n minus 1. 0 to 2 to the power n minus 1. So for 2-bit counter, it counts from 0 to 3. For 10-bit counter, it counts from 0 to 1024 minus 1, which is 1023. Now, there is one issue. The issue is, say, VH of n is this. Now we are getting this duty ratio. And say, next step is this, right? So in between, we cannot get the duty ratio in between. So there is this step, delta D. So we call this delta D. So duty ratio is not smooth. In the case of analog, it is smooth. So it has infinite resolution. But here it has finite resolution, and that finite resolution depends upon the clock frequency that you are using, and that will come in the upcoming slide. So we are counting from 0 to NR minus 1. So the number of steps is how much? 2 to the power n, right? N bit for an n bit counter. So each time period is t clock. And how many such t clocks are there? 2 to the power n t clocks are there. So 2 to the power n into t clock will give me one switching frequency, so which is TSW. And if you invert it, we'll get f clock is equals to 2 to the power n FSW. So this is the condition. Say I want 1 megahertz clock. say I want 1 megahertz clock, FHW is say 1 megahertz, and I'm using 10-bit counter, 10-bit counter, not modulo 10 counter, 10-bit counter. So 10-bit counter will count from 0 to 2 to the power 10 minus 1. So I'm considering 2 to the power 10. So from these two, what is the clock requirement? 2 to the power 10 into 1 megahertz. So that is 1024 megahertz or 1 gigahertz. So that is the clock requirement. So that is the relation between F clock as well as F switching frequency. Now, as I'm mentioning, it has finite resolution, right? It increases in terms of step. So let this be delta D or QDTS. So we are calling it QDTS. So the minimum step in the duty ratio is QDTS because that is decided by the clock again. Okay, someone has asked a question. How to determine a bit for a particular delta V naught. That also I will be telling. In this slide, I'll explain. So the minimum step in the duty ratio is a QD into TS. So QD into, QD into TS is how much? T clock. It is increasing after each clock cycle. So the duration of this counter is T clock. So this is T clock, right? TS or TSW. So from this you will get QD is T clock by TSW. And we know that T clock and TSW are related by this expression 2 to the power n. So we'll get 1 by 2 to the power n. So QD is inversely proportional to n. Here this is n bit counter, right? N bit counter. Say if I want infinite resolution, QD has to be 0. So this should be tending to 0. So n has to be tending to infinity, which is not possible. So if you choose say high counter, like high number of bit counter, say 10-bit counter, then QD will be 2 to the power 10. So whatever may be the value, that is the minimum step in the QD. So if you go for higher bit, then the resolution will be much finer. That's how you decide. Say in the case of buck converter, what is the relation between input and output? Anyone? Hello.
V naught is equal to
Yeah.
D.
V output by V input.
So V output is D into V, right? Say I have given you delta V naught, right? So delta V naught is equals to delta D into V in. So what delta D naught is? The minimum step size in the output that will be reflected for a minimum step size in the duty ratio. Say they have given delta V naught to be say 1 millivolt and V in they have given 12 volt. So what is delta D? And delta D is 1 millivolt by 12 volt. So this is the minimum step size that has to be available in my this DPWM such that it will be reflected in delta V naught as 1 millivolt. So if I consider delta D to be 1 millivolt by 12 volts, whatever may be the value, if that is that can be achieved using my DPWM, then the minimum step size, the increment in the delta V naught will be 1 millivolt. So delta D or delta QD, whatever, is 1 millivolt by 12 volts. So this is equals to how much? 1 by 2 to the power n bit, right? So using this equation, we'll get n. Say, for example, I'm not saying for this example, but say you got n is equals to say 9.56. What counter will you be choosing? 9 or 10? Anyone? Hello. I got from this calculation, say not for this example, any other example, I'm saying say n I got 9.56. Should I go for 9 or should I go for 10? Anyone just tell me what
10.
you may be wrong.
Ten.
So we go for 10 because if you go for 9, 1 by 2 to the power 9 and 1 by 2 to the power 10. So actual desired value is say 9.56, 1 by 2 to the power 9.56. Say for this value, delta V is delta V naught. And for this value, delta V naught 1. And for this value, delta V naught 2. So delta V naught 2 will be less than delta V naught will be less than delta V naught 1. So the recommended is delta V naught. So we should always go with the recommended delta V naught or less, not more. So this is not like we cannot do that because they have given the maximum delta V naught they have given. So we have to go for delta V naught. So we should always go for higher. So if we are getting say N to be 8.56, we'll go for 9. So we should always choose on the upper side. So there is something called ceiling function, right? So we have to apply the ceiling function. So this is about the counter-based DPWM, and as you can see, this is 1 by 2 to the power n, right? So how can I increase the resolution of QD? One thing is I can increase n. So n I can increase the bit counter, or I have to decrease the T clock, which means I have to increase the clock, right? The clock frequency has to be increased. So it needs actually high resolution of clock. So for finer resolution of duty ratio, we need high resolution of clock, which is not acceptable
Hello.
because yes, hello.
Actually, I have some doubt here.
Yes.
What you are saying in the sense, what is QD here actually?
QD is the minimum step size. Say here, this is the counter, right?
Yeah, okay. This is the counter
So
which is counting up to 10. Okay.
yes, so this is the minimum, like in between, if it comes, it will not be reflected here. Say this is one point of Q and this is the other point of Q. In between will not get the duty ratio because
Okay.
this is not smooth. This itself has some resolution issue. So the minimum step in the duty ratio that is possible is QD. And
So that, okay, it's from rising to
yes,
like
say yes,
rising to falling, rising like that. So that
yes,
starting endpoint, that is
yes.
that QD.
Yes. Say I'm saying like in the case of analog, your duty ratio can be 0.1256753. But in this case, it may not be possible. Say it is 0.125, and after 0.125, 0.1250 is possible. Minimum step, right? It has some finite resolution. You agree? So what is that resolution? In this case, it is 0.125
125 is the
resolution
step.
because I cannot get
Yeah.
0.126. I cannot get 0.2 also. This resolution now say in this case my output voltage is 0.125 VA, and in this case my resolution is 0.25 VA. So in between
Okay.
these values I cannot achieve V0 because my DPWM itself is posing the restriction. So I'm saying if you want finer resolution, either one way is to increase the counter size, which is n, or you have to increase the clock frequency.
No, come again one second. Like 0.125, 0.250. So
V. So
0.125
this
is
is the
the
V
in
naught,
between.
right? So because of the minimum step size in the duty ratio, I
Ah,
cannot
mm.
achieve the in between value and the
Okay.
corresponding output. So say that value is D
Oh.
into V. So this D will be reflected in V naught, right? So if this D has some
Mm.
step size, so D is increasing in steps, V naught also will be increasing in steps.
Steps. Okay, suppose if I want 0.127, I can't achieve.
You cannot achieve. Yes,
Right,
exactly.
that's what you're saying. So
Yes, yes.
I can only get 0.250. If I want to get 0.127, I have to like
Increase
increase the
the
like
n value
uh,
so that
n value.
this entire value will decrease. That is one way. Or you can reduce T clock because switching frequency is decided by the converter. I can reduce the T clock. T clock reducing means increasing the clock frequency. But I'm saying the clock
So
frequency
this
is
step,
100
this
megahertz.
okay, this QD you're saying is step size. So
Yes,
this is divided, like this is determined by the T clock by or switching, sorry, F
switching
clock by
frequency.
FSW.
Yes, as you
Okay,
can see, it is counting from 0 to NR. So how many such
okay,
steps are there? 2 to the power n steps are there. And each step has a width of, say, QD.
okay. What is that? Like there is a
QD,
plain
yes.
line, and then
Uh,
you're representing as VHF and on VH
so
of
this is
N,
the
that is discretized.
comparing. Yes, this is comparing. This is coming like this is a V con of S. We are
Okay,
comparing the
so
V con of S with V
above
delta.
that value will not up to count up to that like a trailing edge only till it hits the line, it will
Yes,
count and then it will reset, right? Like
yes,
that you are saying.
yes.
So
So
that
this is
above
giving me
four steps
reset.
will not be counted. So
Yes,
above four
so
steps will
after
not be counted.
until this point is counted, that's why we are getting this duty ratio. Like if I just go back few
Oh,
slides. So this is what.
okay,
So we are discussing about this
fine,
picture here. So I'm
Yeah,
saying
yeah,
this as finite
definitely. So
resolution
whenever it
that
hits,
will,
it's
yes.
yeah.
I'm saying this has
Okay,
finite
then-
resolution because of that it will have this issue. And there
So
is
more finer resolution, if you want, you have to increase the n, or else you can play
increase
with the
the
clock
clock
frequency.
frequency. But for a fixed FPGA, the clock frequency is again fixed. So we cannot go beyond this. So that is one bottleneck of a counter-based DPWM. It will have finer resolution. But
Fine, fine.
again, it is not so like less. It is like it is the resolution is comparatively okay for the implementation that SAR has done. The resolution is okay. It is not that the resolution is bad. We are just
Yeah.
trying to show that it has some finite resolution. What are the constraints to it? So this
Okay.
is all
Thank you.
about
Thank you. Yeah.
yes. Thanks for asking. And this is counter-based DPWM. Now coming to delay line-based DPWM. So in counter-based DPWM, what we are doing is we have counter-based, and we have like counter-based, and then we are comparing it. But here what we do is these are buffer. So each buffer means two NOT gates. So we are creating 2 to the power n buffers. So k here is 2 to the power n minus 1. So we have from m0 to m k. So m 2 to the power n minus 1. So total 2 to the power n buffers are needed. And the mux is from 2 to the power n to 1. So here what is happening? Each buffer will have some delay, right? TD. Such 2 to the power n delays, 2 to the power n delay will say here they're mentioning TC. Such 2 to the power n will give me T switching frequency. So 2 to the power n into such delays. So this is delayed by TD, this is delayed by 2D, this is delayed by 3 TD, and up to so on. And so here, if we are starting with 0, here we will reach TSW. So this is the 2 to the power n into such delay will give me switching. So if I want to find a resolution, then I have to increase the number of buffers with lesser delay. So here what is happening is say our VH is 2. So this is 2. So the duty ratio, so M2, right? So VHN is 2. So it will allow M0, M1 and M2. So this is 2. So until the rising edge of M2, we'll get the duty ratio. So it is nothing but in between the switching cycles, we are fitting n 2 to the power n such say this is M0, this is M1, this is M2, up to so on Mk. Say if VH of n is 0, we'll get the duty ratio from here to here, and if it is 1, we'll get the duty ratio from here to here, and if it is M2, the duty ratio will be from this point to this point. So in this case, the resolution is not dependent on the clock. There is no clock that we are using. The resolution is dependent upon the number of buffers. Say if I increase k, now k is say how much? 2 to the power n. If I increase from 2 to the power n to say 2 to the power 2n, if I double it, then the delay between these has to be reduced and the duty ratio will be much finer. But again, this will also have some issues. The issue is as we are increasing the buffers, if we are increasing say 2 to the power n, right? We are increasing n, the number of buffers are increasing exponentially. So the number of buffers that are going to needed for this implementation are increasing exponentially, and also this delay time, the buffer of this delay time of this buffer, delay time of this buffer, delay time of this buffer may not be same, because it depends upon process and it is not exactly. So the duty ratio is not uniformly increasing, and it has some it is increasing non-linearly. This has some TD, this has some TD plus 1%. And this might have TD minus 0.1%. So it is not exactly TD that it is happening, but there might be some non-linear increment in the delay, and this will have some stability issue. So here the advantage is we can fine tune by reducing TD and increasing, but the issue is the number of input to DPWM will increase. Also the number of buffers will increase, and also the delay time is not uniform. Now, again, as you see, the delay is not linear, as a delay might not be same for all the cases. And this was first come up with people in MIT. So if I want to increase the final resolution, also I don't want clock. See, we have discussed two things. One is counter-based DPWM, where there is a strict constraint on F clock. And here we have strict content of number of buffers, say K. So if I want to utilize both of them, I can do something called hybrid. So it will have both counter-based. It will have counter-based DPWM as well as delay line-based DPWM. Say VCon has 8 bits. I'm saying VCon has 8 bits. So the most significant 3 bits can be used for counter-based DPWM, and the least significant 5 bits can be used for delay line-based DPWM. So what we are doing is, let me change the color. Pointer options. Color, make it say violet. So we are using coarse counter-based DPWM for like coarse increment in the bigger increment in the duty ratio, and we are using delay line based for finer resolution. So how this works, I'll say. So what is happening is we have this increment, right? So this is the counter based DPWM. So from this point to this point is the minimum step size in counter based. So say VLS is 2. So what is happening is it has VMS of n. So VMS of n is going for counter based. So this is going for counter based, and VLS of n is going for delay line based. So what we are doing is VMS of n decides this duty ratio, and within this duty ratio, say now I am maximizing it. Say this is the left line, and this is the right line. So say this is T1, I'm sorry, this is T1, and this is T2. So I'm maximizing it. So it is maximized T1 and T2. So this is T1. Okay, so from T1 to T2, now if we use only counter-based DPWM, I cannot get a duty ratio between this and this point and this point, because that is the restriction of the counter-based DPWM, and because of that, I'm not able to get any duty ratio. Now we are using delay line-based DPWM, and we have say M0, M1, M2, M3, M4 up to so on, say MK, say M0, M1, M2, MK. So what exactly we are doing is we are using a counter-based DPWM, and within each clock cycle, we are using delay line-based PWM. So we'll get finer resolution. So the major thing will be decided by the counter-based DPWM, and in a single clock cycle, the resolution will be decided by the delay line. So now we are using both. So if you see, so the total number of bit is n DPWM. Total number of bit is n DPWM, and for counter-based and for delay line-based. Say this is counter-based, and this is delay line-based. Say we have m bits here, and 2 to the power here n DPWM minus m bits here. So the total is n DPWM. M bits we are using here, and the other rest of the bits we are using here. In counter-based DPWM, we know the equation, right? F clock is 2 to the power n DPWM minus m into F switching frequency. And how many buffers we need? 2 to the power m number of buffers we need. So this is when we are using hybrid DPWM. Now let me tell, if I use only counter-based DPWM, say only counter-based DPWM, only counter-based DPWM, what is the requirement? F clock is 2 to the power n DPWM, all number of bits, into switching frequency. This is when I use only counter-based DPWM, and if I use only delay line-based DPWM, say only delay line-based DPWM, how many buffers I need? 2 to the power n, 2 to the power n DPWM, sorry, n DPWM bits. Say if we are going with this and this, we need very high such requirements. If I'm going for hybrid DPWM, the requirement on F clock is reducing. Also, the number of buffers that are also reducing, and I'm getting finer resolution than counter-based DPWM. So this is hybrid DPWM where they are using counter and delay, and this was also first done like the MIT people has come up with this in 2000. But these are like higher techniques. But in this course, as far as this course is concerned, we are not using these two. We are only using counter-based DPWM, and we are using comparatively high clock 100 megahertz. And the counter is also, I think, sir is using 9-bit or 10-bit counter. So it is comparatively okay. And the resolution is good, not very fine resolution, but it is enough, I would say. So this is all about DPWM architecture. So we have discussed, starting we have discussed some sampling methods. Then I have discussed about voltage mode control, leading edge and trailing edge. And then we have discussed about some DPWM architectures. Now let us go into the fixed frequency current mode control architectures and the sampling techniques that are being used. And then I'll discuss about variable frequency, and then we can solve few problems. So as you can see, I have discussed mixed signal means IL is in analog and V0 is in digital. So we'll be discussing about three architectures today. One is mixed signal peak. So mixed signal I am representing as MS, which is mixed signal. Mixed signal peak current mode control, mixed signal valley current mode control, and fully digital peak current mode control. I'll just briefly explain. So we are sampling V0, which is going to analog to digital converter, and then we are subtracting it from V reference, which is giving me V error voltage, and then it is going to controller, which is giving me I reference of N. So I reference of N is coming from there, and this I reference of N again we have to do it into analog. So that's why we need analog to digital converter. This is in analog. I reference is an analog, and IL we are sensing. So we use resistive sensing, something called resistive sensing. The sensing will be discussed in week 5. At that in that week, I'll be discussing how we are sensing the inductor current. So now we are comparing these two, which is giving me reset, and set is coming from FSW. And this is what trailing edge, right? Or leading edge. This is trailing edge or leading edge. Hello. Hello, can you hear me? So is trailing edge. So this is trailing edge. Let me change pen color. So this is trailing edge, and with interval 2 sampling. Why interval 2 sampling? Again, there is less than a minute. So the meeting will be attended. Meeting will be ended after the. Please join in the same link, and we'll continue from here. So we are taking sample here. So we are supposed to take the sample at this point, but there will be switching noise, right? There will be switching noise, and that's why we are taking somewhat before this. And this is when the inductor current is falling. So this is interval 2. So that's why mixed signal peak current mode control is also trailing edge modulation, and we are considering interval 2 sample with 1 cycle delay. As usual, we are considering 1 cycle delay everywhere. So the implementation, MATLAB simulation everywhere. Sir,
interval 2.
Yes. Okay, let me share my
Sir,
screen.
interval 2 means.
So interval 2 means the off time, basically. Interval 2. Yes. Interval 2.
We are doing the
means
sampling in off time.
Off time. And in interval time, interval 1 means on time. And these are like this terminology is very much important that you should be aware. So we are using trailing edge, means the inductor
Hello.
current is less than reference. Yes.
This fixed frequency method, everything sampling is uniform sampling, but
Yes.
with the interval 2, interval 1 based on the modulation technique.
Yes. Yes.
But
Yes.
sampling is uniform sampling.
Uniform
Right?
sampling. Again, fixed frequency means uniform sampling, and
So, uniform sampling in the sense sampling clock is fixed, so we can't change the sampling clock.
Yes. Yes. And in variable frequency, we use event based.
So here that FSM will be the same value of FSW,
Yes.
but with the
Only it
delay.
is
But
delayed. Yes. Why it is delayed?
that
Because at this point there will
conversion
be a
time,
noise.
computation time. Okay. That conversion plus computation time, that will be later lectures. They will say how we'll calculate and all, or like.
Actually, in every ADC datasheet, they will give you how much time that does ADC need to convert given output voltage. So maybe when we go into that sensing and sampling techniques, I can open a datasheet and I can show you. So we are using
Yeah.
something called pipeline ADC, and it is depends upon how number of stages and how much time it will take.
Yeah.
In our case, I think it takes around 6 to 7 cycles of switching frequency, something like that. I'm not sure,
No,
but that is
my question, like later lectures, they will how we will decide how the conversion and computation is, like in simulated in MATLAB also we will discuss, or like I'm
like in
asking.
MATLAB simulation, it will not take any time because it is ideal ADC. It will
Ideal,
not take any
ideal,
time,
ideal.
but we'll consider 1 cycle delay to mimic the actual hardware. So SAR will be showing all the
Okay.
results for 1 cycle delay. This is not coming from MATLAB. We are deliberately putting this in MATLAB. In MATLAB, if we want zero
Okay.
delay, that can also be done because it is a simulation software, but in hardware
Simulation.
it
Yeah,
cannot be
yeah,
done.
yeah.
So that's why
So
we
like
are
that,
like
my
emulating this.
in while implementing FPGA, you will show the with how the conversion and
Yes.
computational time will be taken, how they decided, and we'll implement, and you'll show the example.
Yes, definitely.
Yeah, okay, fine. Okay, thank you.
Okay. So this is about sorry. This is about the okay. Let me put this. So now we are going to valley current mode control. So peak and valley are analogous to each other. That I can say. So it would be easy for you to also understand. So peak means trailing edge. Valley means leading edge because inductor current is leading. And here we did interval 2 sampling. So here we are doing interval 1 sampling. And so accordingly it will vary. So everything like remains. Say here we are getting reset from the loop. So from the loop we are getting this Q which is reset. Here we are getting set. And in the peak current mode control, set is coming from switching frequency. Here reset is coming from the switching frequency because it is a valley current mode control. And if you see the polarity also, here I reference is plus, IL is minus. Here I reference is minus, IL is plus. So they are just analogous to each other, opposite to each other. One is peak, one is valley. This is trailing, this is leading. Here in peak, we do interval 2 sampling. In leading edge, we will do interval 1 sampling. So this is about mixed signal peak current mode control as well as valley current mode control. So again, this is leading edge modulation as I have discussed with interval 1 sampling. Now, if we go to fully digital, in fully digital, I have discussed there are two architectures. One is very high sampling of ADC so that we'll get the ripple information of the inductor current. This is one. And the other one is we take one sample per cycle and we emulate. And then we emulate the inductor current within the digital FPGA. So we are taking sample of AL. Here, see if you see, this is the sample of IL, right? So using this sample, using this sample, we are emulating. So this blue color is the emulated inductor current. And that emulated inductor current, the sample that has been taken in the this cycle will be used to emulate the current in the next cycle. Because again, this sample is being taken by ADC. So this ADC needs some time, and using that sample, we have to emulate. So again, here we give 1 cycle delay. Now, if we consider mixed signal, IL is in analog, right? IL is in analog and V naught is in digital with 1 cycle delay. So, but here in this case, both IL comma V naught, both have 1 cycle delay.
Hello.
Yes.
One doubt actually in this week lectures,
Uh,
mixed means IL is in analog, current
Analog
in
and
analog, voltage in digital.
digital.
Hello.
Yes. Yeah,
Yeah,
I can hear you.
you're audible, right?
Yes.
Yeah. So here in the waveforms you are showing IL ref, I ref n minus one. So like in mixed signal also after D to A only we will take the compare that put it
Yes.
in the comparator, and so so this should be this, like this value is a digital domain. So if
Yes.
you compare with that, like I'm confusing it,
Okay, okay,
because
okay,
I
okay. So
understood what
you are
theoretically is.
understanding how you are comparing this, right? That is
Yeah,
what your
yeah, yeah.
question.
Like yeah, this
I'll
is
tell you.
like
So,
this IREF will be analog only, after like in the,
no, okay,
I'm
okay,
not saying
okay,
here,
okay.
I'm
But
saying in the
here,
mixed signal itself,
okay,
mixed signal
in the mixed
before.
signal, what they do is
Yeah.
we use another comparator, another IC for comparator. There will be IC.
Okay.
It has two inputs. It will give one output. Say this is I reference and this is IL. Depending upon so we have when we are doing hardware. So this comparator has one positive signal, one negative signal. We are feeding I reference to plus and IL to minus, and this will give us pulses accordingly. The reset pulses or set pulses. If you consider value, it is set pulse. If you consider peak, then it is a reset pulse. So in analog, we needed different specific IC for comparator. But whereas in the case of digital, it is just a code line. Say you want to know whether I reference is greater than IE or not. Say you just want to know this, right? So what I will do is I will subtract I reference minus IE, and then I will consider the most significant bit. So we write everything in 2's complement. So I will check the 2's complement. I will check the most significant bit. If it is 0, then it is positive, means I reference is more. And if it is 1, then it means I reference is like I reference minus I is negative, which means I reference is less than I. So digital comparator takes very less time compared to analog comparator, and it is done in like a single code line. So
uh,
we just do this.
Okay, actually, my question is not this. I understood the process and all. I'm
Yes.
pretty sure, but in the mixed signal, like
Mhm.
IA, like the voltage controller will give the reference value. That is the
Yes.
digital. So
Yes.
you'll put a DAC, and then you'll compare with the analog.
Yes, yes. So
My
this is
question is, in
digital.
every in the this is digital. So this is the only value of IRFN you are showing. Like this IRFN is digital value, right?
Digital value. Yes, yes. I'm showing the digital value.
Then so like actual my question is, how the signal will be after digital converting digital to analog, then we will compare normally, like after this like DA output IRF, how it will be, because every lectures it is compared
Yes,
with the digital value,
yes,
and
yes,
it's like taken the sample. My
yes.
question is, like, because
What
it's
will be
fully
its
analog.
digital value? Okay.
Yeah. So this IRF in analog, how it will be after digital output is coming,
Okay.
is
So
how it will
yes,
be the
yes. I
output.
understood. I understood.
Yeah,
So
that is why I question.
I reference in digital domain, it is constant
Hmm.
for the entire cycle, and then again it is constant for the entire cycle. And
Okay.
in the next cycle, it is again constant. So I reference is only changing once in a cycle in the digital
Once in
itself.
a
Now, even if you
this
change it
is
to analog, it will be the same because analog is the actual information, right? So it will be
yeah
the same in the analog. That's why we have shown the same. So whatever is there in the digital, it will be also there in the analog. But the vice
similar.
versa is
Okay.
not true because in analog, it
Bro,
has some ripple information which we lose in digital. Whereas we are converting from digital to analog, it will be almost same. And since anyway, it is
so
only just a constant value, it will be the same in
okay.
its analog domain.
So that's why you are showing with the digital.
Yes, yes, both are same. And that's why we are
Yeah,
showing this.
fine, fine. Okay, thank you.
Okay. So coming here, so I was mentioning that here both IL and V not have both will have one cycle delay, and this will cause so many stability issues, which is again out of this course, beyond the syllabus of this course. That's why we are not discussing. And also, what is the MC here? MC is the slope of the emulated RAM, and it has some requirements. Else, the loop will be unstable, and the requirement is very high. So when we go for fully digital, there are so many stability issues because the inductor current is also in a digital domain and we are emulating it, right? So this is creating one cycle delay and we are emulating it. So this will pose some stability issues that we are not discussing in this course because it is beyond the syllabus of this. So if you want to go through, you can go through this paper where I have mentioned fully digital for multiple phase, not a single buck converter, but if you want, if you're interested, you can go. And again, here we are taking uniform sample for both V naught of N as well as IL of N with one cycle delay. So this V naught of N will have one cycle delay and this IE of N will also have one cycle delay. that is all about fully digital, just to know, but this we are not going to implement in the hardware because it is somewhat complex and we are not showing. So if you compare fully digital with mixed signal, here we need two ADC, right? One ADC for here and one ADC for here, and only one digital comparator, which is very fast. And here you need one ADC, also one DAC and one comparator, which is comparatively slow. So compared to the digital comparator is very fast. It will take just one clock cycle. So it takes around 10 nanoseconds, but this comparator will have delay. So, and this will give some delay. And here both V0 and IL has quantization. So here more stability issue will come. Here only V0 is in quantization. So comparing these two compared to fully digital, mixed signal will have less stability issue. But here we have more flexibility because both are in digital domain. So we can do whatever we want. So if we want to play with the inductor current, you can play with the inductor current. And since everything is in digital, it is just a matter of code that you have to change, and accordingly it will be changed. And fully digital, even though you may ask me if it has more stability issue, then why are we actually discussing about this? It has stability issues. Also, it has advantage. The domain I am working in is multi-phase, where there will be multiple currents. So one thing we can do is, if we go for fully digital, we can sample everything and we can take in the code. So in the code, if I want to like do some computation for the inductor currents, I can just write the code. Whereas if you put it in analog, you need actual hardware to do whatever you want to. Whereas in the case of digital, it will be just a line of code. And if it has so many stability issues, how to overcome all these are discussed in SAR's paper. So SAR here we'll be discussing about digital current load control, two samplings. Again, this is beyond, so you don't have to go through. I'm just giving a reference. Interested people can go through it. So this is all about fixed frequency. So fixed frequency, we have discussed peak current load control. Sorry, am I audible?
Sir, can you brief on this quantization a bit?
Okay, so quantization is coming from ADC. So ADC will have some quantization, right? Say this is V0. We are taking sample here, and again, sample here, and again some sample here, and again sample here. So we are not actually getting the exact V0. We are taking sample, and there is one cycle delay. And analog to digital conversion will have quantization, because say V0 is 1.25632 volts. But if you convert into digital V0 of n, we might not have this resolution. It will be rounded up to say 2.257 volts. And say the minimum increment in V0 is 0.0001 volts. Say 1 millivolt increment is only possible. So this will be treated as 1.257, right? So it is increasing in the steps of 1 millivolt. So this what we call quantization. In the case of analog, it is smooth. In the case of digital, we have this quantization, which will have some stability issues compared to analog current load control. But when we go for digital, we have so much flexibility. We can change the gains. We can implement multiple different algorithms. See, whatever we are discussing, fixed frequency, variable frequency, a constant on time, constant off time, the entire buck converter, this entire buck converter is same. We are not changing the converter. We are just changing the code in the Verilog and dumping in the FPGA. So using one buck converter and one FPGA, we are implementing multiple control techniques. It doesn't have to be FPGA only. Even using microcontroller, we can implement. So we have that flexibility. If you actually do in hardware, you have to do hardware for fixed frequency current mode control, fixed frequency voltage mode control. The hardware will be different, right? So you have to do that in analog. Whereas in the case of digital, it will be compact. Now we are using FPGA. Say you came up with an IC. It will be very compact in size, and which is a digital. So this is a digital IC. It will be very compact in size. It will be reducing the size, and it will also have flexibility of all the digital controller things. That's why people are moving to digital, because of its flexibility and other advantages. And many commercial ICs are now going into digital. And fully digital is somewhat unexplored, and that's why we have given just a glimpse of it. So if you go to fully digital, what are the stability issues? What are the criteria that we have to consider? all those things, how the architecture changes, how do we implement this, all those things we have shown.
So the analog value, that is called quantization.
Sorry.
Sir, this quantization means we are missing some points of the actual analog.
Yes, yes. So
That
we
goes
cannot
to
get the infinite resolution of V0. We'll get in steps. Say we are using 10-bit ADC, as you have pointed out. Say we are using 10-bit ADC. The resolution will be 2 to the power 1 by 2 to the power 10. Say it is 1.1024. Say I'm nearly taking it as 1000. So 1 millivolt is the step. So minimum V0. Say V0, say V0 is 0.5 millivolts. Say there is an increment in the output voltage by 0.5 millivolts. It will not be detected by this analog to digital converter because the minimum voltage that it will give is 1 millivolt. So voltage V0 of n will increase. V0 of n will increase only in steps of 1 millivolt, and that's why this minimum thing is there, right? So this is what we call quantization, and because of that there are some slight stability issues, but we can still achieve 1/10 bandwidth as well as 60 degrees phase margin, all the design aspects that Sir will be discussing in the upcoming. So I'm saying as we are digitizing it, this analog to digital converter, all this delay, they will have a slight effect on the control loop, some stability issue, but still we can achieve 1/10 switching frequency, we can achieve superior transient performance, all these things that Shah will be showing in the MATLAB simulation case studies, which will be in the week 3. So this is all about fixed frequency. Now coming to variable frequency, I will not go in detail, I will just glimpse, I'll just give a very quick revision of this variable frequency. So here we are discussing 3 things. One is constant on time, and the other one is constant off time, and the other one is hysteresis. So constant off time voltage mode control. So last time someone was asking, why do we need minimum on time? Why do we need minimum off time? So I'll be discussing here. So in the voltage mode control, we are comparing the V0 with V reference, and whenever this gives a positive edge trigger, then we'll turn on the monoshot timer. So it is constant off, right? Monoshot timer will give us say constant off. This is T off, and then T on. But T off time has to be 0 and T on has to be 1. That's why we are putting this inverter. So we'll get T off 0 and T on. So monoshot timer will take time T, and for the time duration T, it will turn on. Say in the case of on time, constant on control, we'll give T on, and for T on duration, it will turn on. In the constant off, for T of duration, it will turn on, but T of duration, we want it to be turned off. That's why we are putting this. So this inverter, you see in constant off in implementation. So I think Sir has already discussed. So in constant off implementation, we use this inverter at the end. So how does it happen? So just let me explain. So after this constant off duration, T off, say V0 is lesser. So V0 is lesser than V reference. So output is 0. And we are turning it on for what time? That we'll see. So this is turned on. Say in buck converter, voltage is gradually increasing. And at some point, it will cross V reference. So at that point, it will increase. So this rising edge will come. So whenever this rising edge will come, the monoshot timer will start off time on and then off. So now we are inverting it. So it becomes 0. So the monoshot timer will give 1 and the Q will give 0. So whenever this event is coming, then we are turning off. And again, after constant off time, we are turning it on and we are waiting for the positive edge trigger. And again, it is happening so on. So the entire working of this is dependent upon this V0 and V reference. Now coming to the point, why do I need minimum on time? So where exactly do I need on time? So coming to that implementation, say after off time, so this is off time, right? I'm sorry. So this is off time. So I'm saying after off time, V0 is less than V reference, and this is 0. But what if V naught is greater than, so V naught is the V naught sample. See, if this is less than V reference, then it is okay. Then it is not having an issue. But if V naught, say this is V naught, is greater than V reference, it is still, so on time has ended and it is still greater than, then what happens? This will be 1, always 1, because it is not going to 0, right? So whenever it is going from 0 to 1, then we can see the positive edge, but it is already remaining in 1. So we will not see any positive edge. So it will not trigger the monoshot timer and it will continuously remain to be on. So QC remains high because V naught is greater than V reference, and Q remains on because monoshot timer is not responding. So monoshot timer output is 0 and Q will become 1. And the inductor current will continuously remain on, and it will, whatever maybe the maximum current, it will reach that voltage, maximum voltage and maximum current, because we are keeping that on time and it is turning on, because we should only turn on when V naught is less than V reference, then only we should turn on, right? Because the voltage is less than this, that's why we are turning on. But if V naught is greater than V reference, why should we turn on? Because the voltage is all anyway above this. Why should I turn on? We should turn off, right? Then the voltage will come below V reference, will fall below V reference, then I will turn on. So this is why we need a minimum T on, because if so at the end of off time, so off time has ended. So this is say off time has ended. Before turning on, there is a logic for minimum on time that Sir has discussed in the previous course. I have given the link over here. So you can watch this video where Sir has explained why we need a minimum of time. This slide has been taken from this lecture. So what happens in minimum on time? So they will check whether V naught is greater than V reference or not. Say V naught is greater than V reference. Then they will provide minimum turn on. They will not completely turn on. They will give some minimum turn on and then again they will turn off. So that's why they provide minimum turn on. For this case, when V naught is greater than V reference, the loop should not go uncontrolled. So only for that case, we provide this minimum turn. I hope I am clear. Hello. Hello.
So can you repeat this?
Yes. Okay. Let me change pin color to red. So what I'm saying is, so let me come back here. V naught is there and V reference is there. So at the end of off time, V naught is say less than at the end of off time, say V naught is less than V reference. This will be 0. So off time has ended. Now we are turning on the Q. So now as we are turning on, inductor current will increase as well as output, will increase. So at some point of time, V naught will cross V reference. So making this QC go from 0 to 1. So this detects positive edge, and monoshot timer gives me T of time on and then on, which will be again inverted, and I'll get off. So my entire motive is to trigger this monoshot timer, right? So, and when will it happen? Whenever this V naught is less than V reference, then only my monoshot timer will be triggered, because it sees a positive edge, right? So this positive edge
Yes.
will come whenever V naught is less than V reference at the beginning of TM. But what if this V naught is not here? What if the V naught is more than V reference, right? If V naught is more than V reference, this QC is already 1, right? QC is before 1 and again it is now 1. So it will not see a positive edge because it is staying at 1, right? So it is staying at 1. So monoshot timer it will not work. So monoshot timer output will be 0 and Q will be 1. So inductor current will increase and V naught also will increase. In V naught is already greater than V reference and it is still increasing, and off time it is not started because this monoshot timer is not triggered. So in this case, what will happen? The voltage will increase and current will also increase. So in order to avoid this situation, and they perform, they provide minimum on time. So at the end of off time, they'll check V naught is greater than V reference or not. If V naught is already greater than V reference, it does not have to turn on. So they provide minimum turn on, which is very less, and that is user interest. So we can give minimum turn on and then we'll again turn off. So that is why we have to check whether V naught is greater than V reference or not. Else voltage and current will exceed. Say in constant off time, because of this issue, V naught and current will increase. And since it is just opposite for constant on time, if we do not provide, here we need what? Minimum on time we need. Here we want minimum off time. So if you do not provide this minimum off time, voltage and current will keep on increasing. And similarly, if you do not provide this minimum off time, V naught and IL will keep on decreasing and it will become zero. That's why at the end of either T off for constant off or T on for constant on, we have to check whether V naught is greater than V reference. If so, we do not have to turn it on. So we'll give minimum turn on and then again we'll turn it off. Similarly, for analogous to constant on time, we'll check whether V naught is less than V reference. If it is less than, then we don't have to turn off. So we'll give minimum off time and then we'll turn on, so that the loop will be stable and the voltage will be regulated. That is the reason why we need this, and how to implement this in MATLAB. That's all we'll be discussing in the next week. So constant off time current mode control. So I'm not going into details because it is exactly same. In voltage mode control, we are comparing V reference with V naught with plus sign, V reference with minus sign. Here also IL with plus sign, icon with minus sign. Why? Constant off time is peak current mode control, right? Peak, it is analogous to peak current mode control. So this is also trailing edge, also peak current mode control. And similarly, for constant off time, we need minimum on time, else either it will keep on increasing or it will keep on decreasing. So this is about constant off time current mode control. And this is the implementation of constant off time, which is also similar to mixed signal peak current mode control, except we are triggering with event. In the case of mixed signal, it is uniform sampling, right? Now as you see, it is event based sampling. So it is interval one sampling, and with 1 cycle delay. Because now it is event based sampling, it will take at this event. So in actual hardware, what happens is there is this gate driven delay. So even it is hitting here in the actual hardware, it will go something like this. So this it will be turned on for some extra time because of the gate driver delay. Because if you give gate driver 0 to 1, it will take time to reflect it and go to the switch. So even though it is hitting the I peak, it will be turned on for some duration because of the gate driver delay. So we are taking the sample whenever it is hitting, right? And it is in interval 1. So this is very crucial. Why it is happening in interval 1 and not interval 2? Because even though it is hitting at this point, because of the gate driver delay, the inductor current will be on for some duration, whatever that gate driver delay is, and then it will turn off. And I am taking at this point, right? So this is interval 1. So it is happening at interval 1 sampling. And since it is variable frequency, mixed signal constant off time, right? This is variable frequency, not fixed frequency. So variable frequency means we go for event based sampling. So that's why I'm saying it is interval 1 event based sampling, and 1 cycle delay. We throughout the course you have to remember that we are going for 1 cycle delay, not TS delay. We will go for 1 cycle delay. And mixed signal constant off is analogous to peak current mode control. So it is also called as trailing, which we can say. Now, if you see the event is whenever this IL is hitting the peak. So at this event, we are naming it as event, and we are using this event everywhere to sample the analog to output voltage. Also, this controller has to update its peak value, right? The controller has to update its peak value once in a cycle. At what event it will update? At this event. So everything in variable frequency, it is with reference to event. So that event we'll be using to update the controller output as well as to sample the output voltage. Now that I have discussed constant off time, as you can see, there is this inverter, because monoshaft timer will give me it will take T off and it will turn on for T of time, it will be turned on, but I want it to be turned off, right? So that's why I'm passing it to inverter. So it will be turned off for T off. Now the exact same thing will be in constant on time. Only we will not find any inverter because we want it to turn on for T on time. So it will not, we don't need this inverter. And again, if you see IL is plus and this is minus, here it will be the exactly opposite. It will be plus, it will be minus. And this is constant on time, we need minimum off time. This is constant off time, we need minimum on time. And constant off time is analogous to peak current mode control. And now this is analogous to valley current mode control. So valley current mode is trailing edge or leading edge? It is leading edge. And that's why it is leading edge. Again, it will not immediately turn on. So it will go for some time because of the gate driver delay. And we are taking sample here. So is this interval 1 sampling or interval 2 sampling? Hello. Hello. Is this interval 1 sampling or interval 2 sampling?
Interval 2, sir.
Yes, right. So this is interval 2 sampling. So interval 2 sampling because we are taking when inductor current is falling, and it is event based because it is variable frequency, and this 1 cycle delay will be throughout the course. And this is leading edge, also valley current mode control. So if you see, both are analogous to each other. Here it is interval 1 sampling, here it is interval 2 sampling. Here it is peak current mode control or trailing edge. Here it is valley current mode control or leading edge. Here we need, here we need minimum on time because it is constant off. And in constant on, we need minimum off time. Minimum off time. So it is completely opposite to each other. So yes.
Sir, in the monoshot timer,
Yes.
The duration for which the input is 1, for
Yes.
that time it will remain in the output of the monoshot timer will be 1.
Yes. So input to say we have monoshot timer. In the MATLAB sir will be showing. So the monoshot timer needs time T, whether it is on or off, it just needs some time T. For this duration, it will turn on. But in the case of on time, this is fine. But in the case of off time, it is turning on for off time, right? It is turning off for off time, but I want the exactly opposite to be done. That's why I'm passing it through inverter. That's why it is off. The working of the monoshot timer is like that it is turned on for the amount of duration that you are giving. But for off time, I don't want that. I want the opposite. That's why we are putting this inverter. And this will also be used in the Verilog coding. So please take a note of this. This is very crucial. Why do we need this inverter? And during implementation in MATLAB, this will be used. And during the implementation in Verilog, this will be used. So just to summarize this variable frequency, we have discussed about constant off current mode control and constant on current mode control. And it is advantageous. It is also advantageous. It has some disadvantages. It has some disadvantages. So how? In the case of constant off current mode control, it is peak current mode control, right? So we need the peak information. So sensing high side current would be sufficient to implement this. The constant off, it is a valley current mode control, right? Valley. So I need the valley information. So I can use the low side sensing. So I need this information. Here I need this information. So here I need a low side current, and here I need high side current. And since off time is constant, on time is coming from the loop. This on time is coming from the loop, right? This on time is coming from the loop. So on time is critical. And in the case of constant on time, off time is critical because on time is already fixed and off time is coming from the loop. So this off time is critical. And we have discussed about minimum on time as well as minimum off time, right? So let me change the color. In color, maybe I'll make it blue. So this has something called minimum on time, and this has something called minimum off time. So during step up transient, so how the inductor current will be there? So inductor current will be like this, and it is constant off time, right? So on time will be variable. So on time can be variable and it can go like this, right? In the case of step down, this is say I naught, and this is also say I naught. In step up case, this is on time is variable, so it can be turned on for any number of cycles. And during the case of step down, it has it cannot completely turn off, right? Why? Because it needs some minimum on time. So for constant off time, it will turn on, minimum on time, constant off, minimum on, constant off, minimum on, constant off, then again it is going. Have you understood this? How I'm drawing these curves? In the case of step up transient, this we call it step up transient. In the case of step up transient, it has to be turned on for a long time. And this is constant off, right? Off time is constant, on time is variable. And here on time is variable. This is T on. It can be turned on for a few number of cycles. Whereas in this case, it has to be turned off for some amount of time, but it cannot be turned off continuously. It has something called minimum on time, which is very crucial. So after off time, we are turning it for less on time, and again we are turning it for less on time, and again turning for less on time, and then it is reaching steady state. The exact opposite thing will be happening in here. So if you consider step up transient, its on time is constant, so it cannot turn on completely. So what happens is this is the inductor current. It will turn on and minimum off, turn on, minimum off, turn on, minimum off, turn on, minimum off, and then it will reach the steady state. And if we consider the step down transient, what is happening? It can be off for any number of cycles because it is constant on, off time is variable. So what happens? It will happen like this, and then it will happen like this. So if you compare, let me change the color. Okay, so if you compare this step up transient versus this step up transient, which is faster? This is faster, right? Because it is completely turned on. Whereas here, this minimum off time is coming in between. Minimum off time is coming in between. Here it is completely turned on. So this is better for a step up transient. And if you consider step down transient, it is better because it can be completely turned off. But here it needs minimum on time, so it is not so superior, and hence it has better step down transient. So it has some advantages, it has some advantages, it has some disadvantages, it has some disadvantages. The further details are discussed in this paper. Again, less than 1 minute is there. If the meeting is ended, please join in the same link. Till this point, if you have any doubts, you may ask me. After that,
Hi, can you explain this a little bit clear? Like
okay.
Yeah.
Okay, so this is constant off, right? So on time is variable. Off time is fixed. And here on time is fixed. Off time is variable. So if you see, whenever there is a load step up, it has to turn on for longer time, right? It has to be continuously turned on for longer time so that the current will increase. And if you see, on time is variable, so this can happen because this much on time can be possible. Do you agree? Hello, am I audible?
Yes.
Okay, so let me continue. So that's what I'm saying. So in this case, on time is variable, right? So from here, we can see that on time is variable. So it can turn on for many number of cycles. That's what we want in step up transient. It has to be turned on continuously. Whereas in the case of step down transient, we need it to be turned off continuously. But in constant off time control, it cannot be turned off continuously because there is something called minimum off time. So after constant off, it has to be turned on for minimum amount of time. That's what we have implemented in the logic. And because of this minimum off time, it cannot be continuously turned off. This minimum off time will come, which will lengthen the step down transient. So step up transient is faster because on time is variable, and we will get continuous on time, and we will not get better step down transient because of this minimum on time. If you now consider this thing, which is constant on time control, here you can see on time is fixed and off time is variable. So in the case of step up transient, what we want continuously on, but on cannot be done continuously because it has fixed time and minimum off time is there. So it will turn on for fixed constant time, off, on, off. So because of this minimum off time, the step up transient is not as fast as this. And if you consider step down transient, we want it to be continuously turned off, and off time is variable, so we can achieve this. So here step down transient
in
is
that-
better. It is
Yeah,
step
yeah.
up
In that,
transient.
I have one doubt.
Yes.
Like if you continuously turn on
Uh-huh.
for a particular amount of time,
Yes.
there will be a collapse in voltage, as you said in previous slide.
Yes,
Then
exactly.
what should be?
So the V
What should
naught
be the
will be
measures?
V naught will be something like this. But
Yes.
we were talking about the collapse without a minimum on time as well as a minimum off time, right?
Yes.
So minimum on time and minimum off time. Now we have connected these in the logic, so it will take care of that, and the voltage will again come back.
Okay.
But if we have not included this, then either the system will collapse to zero or it will increase to it will increase continuously. But now that we have included these two, this can be achieved, and this improvement in the step up transient, step down transient, Sir will be showing the MATLAB implementation in the next week, upcoming week, why it is better, why it is so exact waveforms Sir will be showing in the MATLAB simulation. And if you want to study the constant on time, constant off time digital control implementation, one senior in our lab has worked on this, so you can go through this web. So just to current hysteresis current mode control. So current hysteresis current mode control, as I'm not going much details because we have less time. So here we are having Imax as well as Imin, right? Within this we are controlling the ripple. So this hysteresis has again three control techniques. One is peak, one is valley, one is average. Peak means I reference will be coming from the loop, and valley will be I reference minus delta IL. And valley means I reference plus delta IL, and I reference is the valley. So this is Imax, right? So this is Imax, and this is Imin. So peak means I reference, the peak value is coming from the loop, which is I reference, and the valley we are subtracting the ripple. In the valley point is coming from the loop, and the peak point we are adding the ripple. If you want the average, so whatever I reference we are getting, that is the average. So now we want the peak, which is plus delta IL by 2, and which is minus delta IL by 2. Understood? Hello?
Yeah.
Okay. So these are the three architectures, and if you see here, we need two comparators, right? We need how many? Two comparators. And we are comparing with what? We are comparing with one a digital signal that is coming and with the inductor current. So instead of using two comparators, what we can do is we
Sorry
can
to
use a
interrupt.
bus. Yes.
Yeah, what you are showing is for buck converter.
Yes.
Can we implement the same
for
control
boost
logic
converter
for
as well?
boost converter?
Yes.
Okay.
So the only difference will
For
be the
all
controller.
constant
Yes.
time, constant off also.
Everything can be implemented for any converter. We are showing for buck converter because it would be simpler for you to understand. It is a very basic converter, so it will be very easy to understand. We can do for boost converter, but only thing you have to design the controller accordingly, and the values will change accordingly. In the boost converter, output will be more than the input. So accordingly, you have to change the circuitry, necessary circuitry, but the overall architecture, overall logic, everything remains same. So this is one kind of architecture where we using two comparators. This is another kind of architecture where we are using a single comparator, but we are using mux. So what I mean to say is either we are using reference or we are using valley to compare with the inductor current, right? Either we will use this or we will use this. At a time we don't need both. So we don't have to use both the comparators. Instead, we can use a mux, and this select line will come from the loop. So whether you want to compare the peak current or you want to compare the valley current. So in this case, we need one deck, 1 2x1 mux and one comparator. Whereas in this case, we need two decks as well as two comparators. So it depends upon which one you to use. Here the cost will be less, but there will be some complexity because you have to accordingly select which input will go into the input of the digital to analog comparator. So that complexity is there, but here we only need one comparator as well as one tag. So this is again given in this paper, the same course instructor. So our professor has worked on this. If you want to go through, you can go through, but it is not mandatory. It is up to your interest. If you want to study, then you can study. So summarizing what we have discussed in this lecture. So I have discussed about digital current mode control architectures. One is fixed frequency, and in fixed frequency we have discussed about peak current mode, valley current mode. Average current mode I have not shown. It will be like similar to peak and valley, and they are using uniform sampling because it is fixed frequency. We are using uniform sampling. Whereas in the case of variable frequency, the frequency itself is varying. So I don't want like what do I say? The samples to be taken randomly. I want it to be synchronized with the any event. So in this case, we are using event-based sampling. So for variable frequency, we use uniform sampling. For variable frequency, we use event-based sampling. For fixed frequency, we use uniform sampling. Here we have discussed constant on time, constant off time, hysteresis. Why do we need minimum off time here? Why do we need minimum on time here? And all the implementation will be shown in the upcoming session. So this completes the presentation. Now let us solve some problems. So shall we solve some problems?
Yes.
Okay.
Yeah.
So coming to the problem one, which is based on counter-based DPWM. So this is the diagram. So I'll give you some time to solve, or I'll ask you first. So we need a RAM frequency of, so this is a switching clock, right? Is 200 kilohertz, and the clock frequency I am using is 100 megahertz. So which modulo counter I should be using to implement this? So can anyone tell me how to solve this question? Hello. Okay, if you do not know, it's okay. I'll just tell me to continue. I'll continue because I have explained this concept today itself. Do you want me to? Okay.
We
Or
need
you
to
want to
find
give
the
it right?
Q.
You have to find the n-bit counter. What is the n value? What is the n value? Do you know the relation between FSW and F clock?
The clock is Q times FSW.
Clock is not q times, or yeah, 1 by q times. So it is 2 to the power n times FSW, right? Agree?
Yes.
So clock is how much? 100 megahertz. So 100 into 10 to the power 6 is equals to 2 to the power 6 into, sorry, 2 to the power n into 200 into 10 cube. So if you have calculators, can you tell me what is the value of n that you are getting? So n is nothing but log 2 to the base 100 into 10 to the power 6 by 200 into 10 to the power 3. So this is 10 cube, and this is 2 times, and 2 is 500. So we have n is equals to log 500 to the base 2. So it will be how much? 8 point something, because I know 500 is more than 256, less than 512. So it will lie in between 8 and 9. So whatever value I got, n is less than 8 and 9. So which n bit counter shall I be taking? I'll always go for the higher bit, because then my resolution will be final. So I always go for higher bit. So how much I'm getting? I am getting 9-bit counter. 9-bit counter means it will count from what? 0 to 2 to the power 9 minus 1, right? So it is what? Modulo NR counter, right? So it is modulo what counter? It is modulo NR is how much? 2 to the power n.
10 count.
So 2 to the power n is 512. So it is modulo 512 counter. Understood. So we know from this counter, it is counting from 0 to NR, which is 2 to the power n. So 2 to the power n such t clocks, 2 to the power n such t clocks is giving me 1 THW. So if we substitute with frequency, we will get f clock is equals to 2 to the power n times FSW. And we have given F clock is 100 megahertz and FSW is 200 kilohertz. So by substituting that and applying logarithm on both sides, I'm getting an in between 8 and 9, and I'll always go for higher one. As I told, n should always be the ceiling function. So if you got 8.5, go for 9. If you got 7.4, you will go for 8. So I am going for 9-bit counter, and 9-bit counter counts from 0 to 2 to the power n minus 1, and 2 to the power n is nr. So nr is nothing but 2 to the power n. So which is 512. So I need modulo 512 count. So that only I have shown here. The relation between clock and switching frequency is 1 by nr. nr is nothing but 2 to the power n. Is this question clear?
Yes.
Everybody, if you want me to repeat, I will repeat. So shall I go for the next question, or shall we go for this? Like, shall I
Sir,
repeat?
this NR,
Yes.
sir, this NR counter counts from 0 to 512.
Yes. So actually, there are two terminologies. One is n-bit counter. N-bit counter means it is counting from 0 to 2 to the power n minus 1. And modulo nr counter means it is counting from 0 to nr minus 1. So in the question I have asked modulo counter, which modulo counter I need. So it is counting from 0 to 511, right? So I need 512 modulo 512 counter. I need modulo 512 counter. But if I ask which n-bit counter I need, so n is what I am getting from here, n is 9. So I need 9-bit counter. So the terminology is very important. Modulo counter is different and n-bit counter is different. So depending upon the question, you will get the value. Both are related. So nr, modulo nr counter and n-bit counter, they are related by this expression. So they are related, only the terminology is different. So you should be aware of this terminology. So is this question clear?
Yes.
Okay, so let us move on to the next question. So next question, I have given what is the delta V naught that can be achieved for V12. Again, I have discussed this in the today's class, where I have told delta V naught is what? Delta V naught is delta duty ratio into Vn, right? So now delta V naught is what? Delta duty ratio into Vn is 12 volt. And how much is the delta D? So this is the delta D, right? Delta D. How much is the delta D? Hello.
T clock by TS.
Yes. So, right. It is T clock by TS into 12. So this is the delta V naught. So this question is the continuation of previous question. So I have given 100 megahertz clock, 200 kilohertz. So what is that? So this is 100 megahertz means 1 by 100 megahertz. And this is 200 kilohertz. So 200 kilohertz into 12. So this is what 10 to the power 3, 2 times 500. So delta V naught is 12 by 500. So if we do into 2 by 2, it will be 24 by 1000. So it is 24 milliwatt. So for this given DPWM, the minimum like the delta V naught that is possible is 24 milliwatt. So it is just the same thing. I am representing in terms of delta V naught. If I ask in terms of delta D, then delta D is how much? 1 by 500, which is T clock by TS. But I have framed the question in a different way, which might seem a bit difficult, but it is not difficult. I am asking in terms of delta V naught. So I have mentioned it is a buck converter. So for buck converter, delta V naught is delta D into Vn. So delta D I can get from T clock by TS, which is 1 by 500. And the delta V naught is delta D into Vn. So 1 by 500 into 12, which is 24 milliwatt. So I am just framing in a different way, but the basic concept is the same thing. Understood.
Sir, what if that converter is a boost converter?
If it is a boost converter, then what will happen? So If then I cannot directly ask V naught because V naught is D by 1 minus D into V in, right? So we have to see how much the minimum variation happen in this. It is not straightforward. That's why I have not asked in boost converter. Here it is directly proportional. That's why I have asked in boost converter, because now V naught will be delta D by 1 minus delta D into V. So you have to do this. And it is not straightforward. And it is a non-linear, right? Not linear function. So that's why I have given you linear function.
Is this what question?
This is buck. This is buck. Sorry, there is no D. Sorry. Thanks for correcting me. 1 minus delta D. But it will not give the delta V naught because you have to see what value it is giving. And it is non-linear. That's why I have not given. But still you can solve. So how much value that you are getting, we have to see. But I don't think this will be giving delta V naught. No, this will not give delta V naught. Because it is inversely proportional. Here it is directly proportional.
Can you explain that modular duty cycle resolution formula once, because I am absent during that?
Okay. So this modulo counter is counting from 0 to nr minus 1. Say we are considering n-bit counter. You know, any n-bit counter count from 0 to 2 to the power n minus 1. So now you can understand nr is nothing but 2 to the power n. So we have from 0 to nr minus 1. Each duration is t clock. Here we have given each duration is t clock. And the overall duration is TSW. Overall duration is TSW. And how many such steps are there? 2 to the power n such steps are there. So 2 to the power n such steps are there, each with the time period of t clock. And it gives me the total time period TSW. Now if I make it 1 by f clock, 1 by FSW, then I will get f clock is nothing but 2 to the power n into FSW. So this is the relation between f clock and FSW. And here I have twisted the question and I was asking delta V naught. So you have to convert this delta D into V naught by multiplying by V because it is a buck converter. And boost converter, it is not straightforward, and that's why we do not ask because it is non-linear. And that's why we do not ask for boost converter. And we'll only ask for buck converter because it is linearly proportional to delta V naught. Understand?
Yes.
So, so the same formula which was discussed in the previous question can be applied for this question as well, but we need this extra V. Now, hybrid DPWM. Say hybrid DPWM is 8-bit. I have given it 8-bit, and 3-bit I am using for DPWM, and 5-bit I am using for delay line based DPWM. This is the background story. Now the question is, what is the relation between FSW and F clock? Can you tell me? And modulo counter is 3-bit. This is 5-bit. The same formula which we have used in the previous slide. Hello. Hello. Hello, sorry. So using the same formula, F clock is 2 to the power n times FSW. Same formula. Even though it is hybrid, this part is counter based PWM, and the concept is same, right? We are this is n bit. Now we are using how much bit? We are using 3-bit. So we have given 3-bit. So the entire basic concept remains same. You might think that okay, these are two coming are picture, so this might not be different. This is complex more. The entire the basic concept is same. In a DPWM counter-based DPWM, if you are given F switching frequency, F clock is 2 to the power n times switching frequency, and here it is 3-bit. So F clock is 8 times FSW, which is 2Q. And how many buffers are needed for this hybrid PWM? So how many buffers? So these are buffers, right? How many such buffers do we need in this question?
for m.
Sorry.
This 2 for m minus 1.
Okay, so what is M?
Number of buffers.
No, M is not M number of buffers. M is number of bits. And what is the number of bits?
5.
5. So
Five.
we need 2 to the power 5. Actually, M0 to MK. So we are representing it as 0, 1, M0, M1, M2, up to so on M2 to the power 5 minus 1, which is equals to M31. But this is 1, this is 2, this is 3, up to so on 32. So we need how many buffers? We need 2 to the power M, which is 2 to the power 5 buffers. So we need 32 buffers for delay line based DPWM. So it has actually 2 parts. You should not get confused with the 2 parts. So one part is the delay line based PWM, and the other part is the counter based DPWM. So counter based DPWM, as the number of bits are 3 bit, F clock is 2 to the power 3 into FSW. So this is 2 to the power 3 into FSW. So we get 8 times. So clock frequency is 8 times switching frequency. In the delay line based DPWM, it is 5 bit. So it is 2 to the power M is to 1. So 2 to the power 5 is to 1 mux we will be using. So it is 32 is to 1 mux, and that's why we need 32 buffers. So that's why we need 32 buffers. But the naming is M0 to M31. So if you total count it, it will be 32 buffers. So is this question clear? Hello? Or you have any doubts? If you have any doubts, I will repeat. Is this clear? Hello?
Yes, sir.
Okay.
Yes, sir. Yes, sir.
Okay. So now coming to this architecture. So is this analog or mixed signal or fully digital? So first of all, is this analog?
Yes, analog.
How are you saying it is analog? This is what?
Analog to digital.
So is this analog? This domain is digital domain, right? Because it is getting converted to analog to digital. Isn't it?
Yes.
So is this analog then? Hello? Hello?
It's mixed signal. It has both analog and digital.
Yes, but analog means it is, yeah, you are right. So analog means pure analog, mixed signal means analog plus digital, fully digital means fully digital. Now tell me which one. Is it analog, mixed signal, or fully digital?
Mixed
Signal. Analog means purely analog. Fully digital means fully digital. Mixed signal means V0 is in, so this entire part is in digital domain, right? So you are right. This is digital and this is V0. V0 is in digital domain, and this is, if you see, current. This is in what? Analog domain. So that's why it is mixed signal, not fully digital, not analog. Now the next question is it fixed frequency or is it variable frequency? So can you recognize this? So we have IV of n, and we have IB plus I delta IH. So this is like I minimum, and this is like I maximum. So this is current hysteresis control, right? Because we are like regulating the delta IL. Understood?
Very good.
So yes, right. You are right. So this is not fixed frequency. This is variable frequency. Now, is this constant on or constant off or hysteresis control? Which control is this?
Hysteresis.
Hysteresis. So not constant on, not constant off. It is hysteresis control. And is this voltage control or current control?
current control.
Current control. Because as you can see, there is inductor current here, and it is current control. Now, is this peak or is this value or is this average? From this, you can say
Average.
Valley. Or...
Okay, let me go back. So it is valley current mode. So that's why this. See, valley, the minimum is coming from the loop I reference, and we are adding delta IL for getting Imax. For peak, the peak is coming from the loop, and we are subtracting ripple to get I minimum. For average I reference, we are adding delta IL by 2 for getting Imax and minus delta IL by 2 to getting I minimum. So now coming back to the question. Here IV, this IV of n is coming from loop. I am adding delta IH. So the value is coming, peak I am getting by adding delta IH. So this is not this is not peak because value is coming, and this is also not average. So overall it is what? It is a valley mixed signal hysteresis current control. So you have to be this much confident about the architecture. So looking at the architecture, should be able to tell which is valley current mode or peak current mode control, or fixed frequency, variable frequency, voltage mode, or current mode. You should be this much confident and strong about the basics, all these architectures, and these are very crucial. Like not here in anywhere, say if you join in a company, they'll say like we are using constant on-time current mode control. They will not give you this diagram. You should be able to understand, okay, they're using constant on-time current mode control, which means it is a variable frequency, and they'll not use uniform sampling, they'll use event-based sampling, and on-time is fixed and off-time is variable. So, and there will be minimum on-time circuit as well. So all this architecture you should be having in mind, and you should be very thorough with all these architectures. So this is one example. Okay, I have a question here. Sir, how is it variable frequency? Yeah, that is a good question. Coming back to this hysteresis control. So I'll be explaining here. So who is deciding this on time? Until it hits this peak, it is turned on, right? So I am not deciding this on time. And whenever this inductor current is hitting this ripple, then only I am turning it off. And who is turning it on? Like who is deciding this off time? Again, the loop is deciding, right? I am not deciding. I am not giving constant on time. I am not giving constant off time. I am making it increase, and until it hits, and after that it hits, I am turning it off. And again, when it hits the value, I am turning it on. So now what happens? I'm not sure what is this on time. I'm not sure what is this off time. Both are dependent on the loop. So this is variable, off time is variable. So on time is variable, off time is also variable. So both on time is variable, both off time, so both on time and off time are variable. So neither of them is constant. But what is constant? The ripple. We are maintaining the ripple to be constant. Delta H is always constant. So that's why on time is variable, off time is variable. That is why this is variable frequency. And actually, this is a good question, as you have pointed out. Okay, let me change the color. Let me change it to say yellow. So in constant on time is fixed, off time is variable. Constant off time is fixed, on time is variable. Hysteresis, both on time and off time are variable. Ripple is constant. Okay. So let us move to the last question. So again, is this analog or mixed signal or fully digital? Sorry?
This mixed signal.
Mixed
Mixed
signal. Mixed signal, because it is not fully digital, because I can see the inductor current is in analog domain and the voltage is in digital domain. So it is mixed signal architecture, whatever it is. So is it fixed frequency or variable frequency?
Variable frequency.
Variable frequency. Because I can see there is something called minimum off time, and there is something called event here, and everything is done with respect to this event. So I know that this is event based sampling, and that's why I can say that it is a variable frequency. Now the next question is it constant on time or constant off time or hysteresis control?
Constant on time.
Everybody agree? I know that this is not hysteresis control because there is no delta IH. I'm confused between constant on time or constant off time. So how can I say that whether it is constant on time or constant off time? How can I say?
Minimum off time is required for constant on time.
Yes, you are right. So minimum off time is required for constant on time. So it is not constant off time either. And also you can see this plus sign and minus sign, right? So
Comparator is
This is peak.
this is value
it's
actually. Value. So whenever IL is going less than I reference, it will trigger. So this is valley current mode, also leading edge. So that's why it is constant on time. Now the last question is it voltage control or current control?
current
It's
control.
current control.
Because I can see there is a current that is being compared with the reference. And is this peak or value or average?
Really.
Value. So this is not peak, this is not average, this is value. So overall, which sampling is being used here, uniform or event?
Event-based.
Event based. See, if you see, there is only one architecture, but there are so many terminology that you have to be very clear. Should be clear whether it is analog or mixed signal or fully digital, fixed frequency, variable frequency. Here I have given you nothing. I have just given you one diagram, but you can see, if you can see, we are getting a lot of information from this picture. I'm able to detect whether it is constant on or off. And I can also say that it is current mode control. And from this, as it is constant on time, which is analogous to valley current mode control, I can say it is valley current mode control. And it is not uniform because using this event, I'm triggering everything and I'm taking sampling. So this is event. And is this trailing edge or leading edge?
Leading edge.
Leading edge, because valley, I know that current will lead I reference. So that's why it is leading edge. So it is a mixed signal, constant on time or leading edge time current mode control with event based sampling. So this is the architecture of this. So you have to be this thorough. So whenever you are preparing for your assignments or exams, you should ask yourself. So you can ask these questions. I have tried to put a maximum number of questions that I can ask in this from this architecture. So you can ask these questions whenever you are preparing. So you can take constant of or hysteresis current control. You can ask whether it is analog, mixed signal or fully digital, whether it is fixed frequency or variable frequency. So if I have considered variable frequency for both the examples. So if it is fixed frequency, is it peak or is it valley or is it average? Is it voltage or is it current? Then which sampling is being used? Is it trailing edge or leading edge? So all these questions you can answer. So in average control, there is no such trailing edge, leading edge because it is average. Only peak and valley have this trailing edge, leading edge. So in average control, there is no question as such trailing edge or leading edge. Is the concept clear? So sorry, is the concept clear? How to
Yes,
get? So you have to be very clear and confident about this terminology. Constant on, constant off. Mainly this trailing edge, leading edge, peak current mode control, valley current mode control, and when do we use event based, when do we use uniform sampling, and which is mixed signal, which is fully digital. Because current is in analog domain, it is mixed signal. If current is in digital domain, then it is fully digital. So these questions might be asked in your assignments or in the exam also. So that is all about this
sir, one
session.
one
If you have
more
any
doubt,
doubts,
sir.
you can ask them.
Yes, sir. So not about this problem.
Okay.
This is the first time we are appearing for we are participating in NPTEL. So
Okay.
this is the first examination we are going to write.
Okay.
So how the questions will come and what is the pattern? Such things.
So every week there is something called assignment solving, which carries some marks.
That I know.
So okay, okay, maybe I'll write it here. So there are first thing is assignments. So assignments are completely based on the lecture videos. So if you are thorough with the lecture videos, if you are aware of all the concepts, say in this week, if you consider, Sir has not discussed anything other than sampling techniques as well as digital control architectures. But if you see, there are so much information that is there in like one architecture. There are so many questions that can be asked. So you have to be clear with all the terminology, all the counter-based DPWM, delay line-based DPWM, hybrid DPWM, and then fixed frequency digital control architectures and variable frequency control technique architectures. And so when you are prepared with assignments, then the question paper will be based on assignments only. You can expect a similar type of questions from assignments. If you are thorough with the assignments, 80%, 80 to 90%, you can solve the question paper. The other 10%, it will be tricky. You have to be very confident about all the concepts. So for this 10%, you should be very thorough and solve as many problems as possible. So
Okay,
if you
okay.
are thorough with the lectures, if you see, you will see no assignment question will be out of this lecture. All the assignments are based on lectures, and all the questions in the question paper are based on assignments, except 10%. Usually we give this 10% questions to like differentiate between students. Like we usually keep these questions to test the understanding of the students. So I recommend you to go through the lectures completely. Also in these practice sessions, I'll be first giving an overview of what Sir has discussed. So if you face any difficulty in understanding the concepts, I'll be clearing that. So in my problem, sorry, I have to select it. So in my problem sessions, there will be two parts. One is I'll be discussing about theory, and then I'll solve some questions. But if you see the questions, I can solve more, but only when you understand the theory completely. So like the questions I can frame for constant on time or constant off time, but only it happens if you know the theory clear. So that's why I have spent more time on theory. So these are the beginning weeks where theory is the building block for which you can solve the questions in the upcoming weeks. So this theory should be very clear. All the architectures, all the nomenclature, all the naming, everything should be clear. So Sar will be discussing in his lectures, and the TS will be giving the assignments, which will make sure that you understand all the concepts properly. But on the other side, I'll be also discussing theory part, and also I'll be discussing the questions, so that I'll help from my side to make you understand the concepts in a better way. And if you have any questions, you cannot ask Sir, right? You can interact with me, any type of questions, I'll try to answer.
Thank you, sir. Thank you
Yes,
so
sir. I
much.
joined very late today.
Okay.
Whatever you presented today, whether it will be available?
Yes. So
As a
last
material?
week it got delayed, and I have uploaded on Wednesday. This week I'll be uploading by tonight. All the videos will be clubbed into a single video, and the Google Drive link, I think it has been shared, where I'll upload all the information, PPT, all the information I'll be uploading there. Again, there is a less than 1 minute, so I'll try to wrap up. So in this lecture, we have discussed about sampling methods and fixed frequency, variable frequency digital control architectures, and different types of architecture, and we have solved few problems as well. I will try to upload the video by tomorrow night time, so you can check my channel where I'll be uploading the videos. So, and I think they have shared the drive link with you, where I have mentioned all the lecture notes, and I have uploaded them. If you have any questions, and if this meeting ends, please join in the meeting so we can discuss. Do you have any questions?
No, sir.